This is Chapter 8, Part 2. So we left off at the bromine test for unsaturation. So halohydrons can be formed as well. Anything with a halogen with an OH group is a halohydron. Here are examples of chloro, bromo, and iodohydrons. So if a halogen is added in the presence of water as a solvent, a halohydron is formed. Water becomes your nucleophile. This is a Markovnikov addition. Again, you need to note this. The bromine or bromide, the electrophile, will add to the least substituted carbon, and then the water will add to the most. In terms of mechanism of formation, you have your source of electrons doing nucleophilic attack, forming the halonium ion with the halide. And then you're going to have water come in as your nucleophile, attack that most substituted carbon, opening the ring so that you have now X and water. That water isn't done because it's positively charged. You want to pluck off that hydrogen. Charges go to the oxygen to neutralize it to form your halohydron. Again, it has Markovnikov orientation and it's anti. So because this was coming on the backside, so you have to have anti-addition. If we look at an example of cyclopentene reacting with bromine and water, we generate the trans-bromocyclopentanol, as well as an enantiomer, which I'll show over here. So instead of the bromine going on the top, it goes to the back, and then your OH goes to the front. So that's the other enantiomer. Okay. So orientation of the halohydron formation, again, like I had said, the water, after your hydronium ion is formed, the water will attack the more substituted carbon. So this has methyl, whereas this has two hydrogens. So this is going to have a more positive delta because of the fact it's more stable and it's more substituted. And so the water is going to attack the more substituted side, open up the ring so that it generates the halohydron. Well, this will be then deprotonated by water. So when you generate this will give you the Markovnikov product at the end. An important thing is that the opening of the halonium ion is driven by its electrophilic nature. So the weak nucleophile attacks the carbon bearing the more positive charge, which is more substituted. Okay. Let's do a problem. So propose a mechanism for the reaction of 1-methylcyclopentene with bromine and water. So draw out 1-methylcyclopentene. It's shown like this. And so the first reaction is with the dibromine. So here you have nucleophilic attack onto the bromine, kicking this off, generating the bromonium ion. Now you have the possibility of water attacking either this carbon or this carbon. In this carbon you have methyl group and this, so this would be a tertiary carbon. In this case you have a hydrogen, which would make it a secondary carbon or slightly positive carbon. And so this will have the more positive charge as a result. We'll attack that side, open up. Now once it's generated, it'll pluck off the water in the solution, will pluck off the hydrogen, neutralizing it, generating this. And the other enantiomer, which should be with the hydroxide on the backside, methyl group coming out, and with the bromine coming out. So that would be the other enantiomer. Let's do another problem. When cyclohexene is treated with bromine in saturated aqueous solution of sodium chloride, a mixture of trans-2-bromocyclohexanol and trans-1-bromocyclohexane results. Propose a mechanism to account for that. So the first step, you have your cyclohexene, you have your dibromine, right? This you should show. And then you have attack, right, from your nucleophile, which is double bond, forming the bromonium ion shown here. Right? Once the bromonium ion is shown, you have water either attack or chlorine attack. So let's do chlorine first. From the sodium chloride, we'll attack the more substituted carbon. In this case, it's symmetrical, so either one is fine. Kick off the bromine, generating the trans-bromo-2 cyclohexane. The other is the water. Water will attack like it should, again in the same way. And then kick out the bromine, and then you're going to have deprotonation of the water and generating this. Again, you should show both enantiomers, right? So this in addition to the other enantiomer, this in addition to the other enantiomer. I'm not going to go through that since I've already done it in the previous example, so you should be able to do that yourself. Now there's catalytic hydrogenation of alkenes. Catalytic hydrogenation is when you take an alkene in the presence of hydrogen and catalyst, platinum, palladium, or nickel, it will reduce this double bond to a single bond. We talked about this actually in class doing a problem for problem set 6, I believe. So you should be familiar with it. And I didn't specify the catalyst, but now you know which catalysts are in play. So now hydrogen in the presence of any of those 3 catalysts, in this case platinum, will reduce it so that it's a completely single bond. This reaction only takes place if the catalyst is. So mechanism for this, so what happens is you have adsorption of the hydrogen and the alkene on the metal surface. So you have a metal surface, draw the metal surface. You have hydrogen, oops, sorry. We're going to draw the hydrogen again. You're going to have hydrogen adsorbing on to the platinum. Let's say this is the platinum surface. So they're both on the same side on the platinum. As a result, when it comes and reacts with the double bond, it can go on top or on the other side, on the bottom of that double bond. So if it comes on the bottom, or at least in this case on the bottom, you're going to have syn addition, so it's syn stereochemistry. They'll add on the same side of the double bond, and then it will produce, or the reduced product, which is here. So you can have this coming in from the bottom side as well as it coming in from the top side. So I'm going to show, hydrogens, and then the deuterium in the back. So these two are generated, right? Because you can go on the top or the bottom face. You can actually use a chiral catalyst. An example of this is this ruthenium binap chloride. It's shown as this. So with this and one equivalence of your hydrogen, it will react with this double bond and hydrogenate on the back side. So it'll come to the back side, so then the hydrogens will come on the back side. So as a result, the methyl group gets pushed to the front, and it generates this product with 96% EE. And so this allows for just one enantiomer to be formed, whereas in the case of the previous, where just platinum or palladium or whatever, you generate both possibilities. Again, why is there a need for chiral catalysts? So for dopamine to be generated, you need the S form of dopa, shown here, and the only way to generate the S form of dopa is from this alkene in the presence of one equivalence of the rhodium diop catalyst, which is a chiral catalyst shown here. It will add the hydrogens to the backside, right? And then as a result will generate the S-dopa, and then in your brain it'll be able to cross the blood-brain barrier, and so your brain will then, through enzymes, convert it into dopamine. Carbenes can also react with alkenes, and the mechanism for that is shown here, where your electrons from your alkene goes to the carbon, and these electrons come to the other carbon to generate cyclopropane. So it's essentially an insertion of the CH2 to generate the cyclopropane ring. There are 3 methods: diazomethane, Smith-Simmons, and alpha elimination. So in terms of the diazomethane method, here's diazomethane on your left, and then you have a resonance structure in which your electrons from your nitrogen come in, forming the triple bond, kicking this off, right? So that was what was missing in this resonance structure. Again, your brackets are here and your double-headed arrow. And so here is the one that's reactive. When you generate this version, you see that this nitrogen as nitrogen gas wants to leave. As a result, your electrons go, generating the carbene, reactive carbene, and then it'll insert into C bond. There are problems with diazomethane. They're extremely toxic and explosive, and the carbene can also insert into CH bonds. So for the Smith-Simmons reaction in preparing carbenes, you have CH2I2 in the presence of zinc copper amalgam, generating your Smith-Simmons reagent, which is ICH2ZnI. In the presence of an alkene and the reagent, you generate cyclopropanes. And so essentially it is in generating this Smith-Simmons reagent that allows you to generate the carbene and allows you to form the cyclopropane. The other is alpha elimination in the presence of bromoform or chloroform and potassium hydroxide or base. What will happen is, let me show you, this will be C, we'll put the H over here, Br down here, sorry about my handwriting, please bear with me, and your other Br. So this is your bromoform. So in the presence of your base, you're going to have electrons from your oxygen pluck off that hydrogen, right, and form, and have the electrons go to the carbon, forming this intermediate right here. This will then want to have one of the bromines dissociate to generate the dibromocarbene, and this is what reacts. So in the reaction, that will form a cyclopropane. What's important is stereospecificity for these reactions. If you have a trans alkene in the presence of, this is chloroform, you're going to generate the cyclopropane, but the stereochemistry of that trans system still remains. If you have it in cis, this is bromoform, again, the cis stereochemistry remains. Here are some examples of carbenes, Smith-Simmons reaction. Again, here's the reagent. You're just going to have to memorize this. It generates at the alkene site cyclopropane. If you do alpha elimination reaction with a bromoform in the presence of base, you generate the cycloalkane, but note that it has the bromines attached. If you use chlorines, it would be chlorines attached. Please don't forget about that. Epoxidation. So epoxidation can happen with alkenes. Epoxidation requires the use of a peroxy acid. So it's an acid with an additional O, so that's why it's called peroxy acid. And it forms what is called an epoxide. It's like that cyclopropane, but instead of a CH2 or a CBr2, you have over here an oxide. It's called an epoxide or an oxirane, and then it generates an acid. So here the alkene reacts with the peroxy acid, forming the epoxide. Most common peroxide used is metachloroperoxybenzoic acid, which you should memorize, and the structure you should know as well. Now, the mechanism. So the mechanism is deeply tied with how you draw out the peroxy acid. So you want to draw out the peroxy acid where the carbonyl is here and the oxygens are here and the hydrogen. So essentially you want the oxygen over here and the hydrogen over here and this sort of five-membered potentially ring structure. And so if you draw this correctly, then drawing out the mechanism is easy. So again, your electrons from your oxygen go over here, this moves around, the oxygen plucks off the hydrogen, and this comes down to form this transition state. Now that should be double dagger. Please do not forget to put a double dagger in your transition state. Here's your transition state is formed, and then what happens is your product is your peroxide, or not peroxide, your epoxide, and then your acid. So once this is formed, you generate these two products, and it happens in one step. It's a concerted mechanism. So stereochemistry of epoxidation. Here's MCPBA, which I told you have to memorize. So you should know the structure, and you should be able to take the structure as in the previous page and draw it out so that you can do the reaction, epoxidation reaction mechanism. So if you have a cis where the two methyl groups are on one side, it will retain that cis stereochemistry and the epoxide will be generated. So the epoxide can be generated on top of the bond, right? Or on the bottom, right? So you'll generate the top or on the bottom. Either way, you'll generate the same stereochemistry, and you'll have the cis maintain. If you have a trans system, you have epoxides again, formation coming from the top or from the bottom. So you can have this as well as, I'm going to draw it out with the methyl groups, the epoxide going on the bottom. So here you have hydrogen, here you have hydrogen, and so this is the other enantiomer that is formed. So when you're writing out these reactions, make sure you're noting if there's enantiomers, whether the enantiomer is being formed to get full credit for your exam. Now, opening of the ring epoxide. So after you've generated your epoxide with the peroxide, you can then open those rings in the presence of acid and water. So you generate a hydronium. The oxygen will pluck off that hydrogen from the hydronium to generate water. So in reality, let's draw out the hydronium so that when you draw these mechanisms out, I want you to show all of this. So essentially, the electrons from that will pluck off a hydrogen. This will quench that, so you generate water. Now you have this protonated epoxide in which the rest is the same. The water will attack on the opposite side of the epoxide, so the back side. And then once it attacks, it'll kick out, forming the hydroxide on one side, this protonated hydroxide over here. You want it to be neutral, so water will come in, deprotonate that, quench that positive charge, so now you have this trans diol. So it's important that when you're adding water to an epoxide, you're going to have anti-diol that is being formed because it has to happen from the backside. For syn hydroxylation of alkenes, so in the previous case you have anti-formation. In order to get syn addition, you have to use a different type of reagent. The two types of reagents you can use are osmium tetroxide or potassium permanganate in the presence of hydroxide. So we're going to look at osmium tetroxide. So in the case of osmium tetroxide, for the mechanism, the key is to put the osmium tetroxide in an arrangement that allows you to draw your arrow so that the mechanism is rather straightforward. So here you want to make sure that the oxygens from the osmium are right on top of where the carbons are, of the carbon-carbon double bond. Once you have that, again, your electron source is from your double bond to the oxygen, electrons push to the osmium, and then these electrons get pushed on to the carbon. So here you generate an intermediate, which is the osmate ester, and in the presence of peroxide, or this reagent over here, it'll cleave off the osmium so that you generate your glycol. So osmium tetroxide adds across the double bond of an alkene in a concerted mechanism forming this osmate ester. The osmate ester will be hydrolyzed to form the cis glycol. So again, this is on the same side, so it's cis. For permanganate, same thing. The mechanism is crucial, and the way to draw the mechanism properly is to make sure you position the manganate relative to the alkene in the right way. So if you have the double bonded oxygens right where the carbon-carbon are, then it makes it easy because, again, electrons from your double bond go to the oxygen, electrons from that double bond go back to the manganate, and then here your double bonded oxygen electrons go over here, so that you generate the same type of molecule except as the osmium tetroxide, except you're using permanganate. And then in the presence of hydroxide and water, it'll cleave this off, forming the cis glycol. Interestingly, in this case, the manganese dioxide that is formed as the product will precipitate, and so you know that the reaction will occur when this precipitation happens. So this is important. The reaction for this dihydroxylation for syn addition must happen in cold dilute solution of potassium permanganate. If the solution is warmed or acidic or too concentrated, then you can have overoxidation where you have oxidative cleavage. This will result where you have disubstituted carbons becoming ketones and monosubstituted carbons becoming carboxylic acids. This is important. So if we look at the mechanism, so we already, as you already know how to draw the mechanism to form the glycol, we're going to start off from the glycol over here, right? Now this is warmed and concentrated, so you're going to do the same mechanism as before, generating the glycol. Because it's warm and concentrated, this will then overoxidize where you have cleavage of this bond, right? So essentially you're having oxidation where you're having cleavage of this bond, this forms, this, and this gets kicked off. The bond gets kicked out to form a double bond over here, so you have ketone as well as aldehyde. That aldehyde then gets overoxidized into the acid. So wherever you have an H, right, that H on the other side will insert an oxygen in front of the H. So let's look at examples. Here's an example of an alkene. You're going to see cleavage over here. So in this case, this will generate the ketone, right? And this side will generate, because it has that H. Sorry, I'm going to draw that H. That H, you're going to insert an oxygen in that H so that in this side you're going to generate the acid. Same thing here. Now you have two alkenes, one here and one here. In this case, you're generating the ketone. And on the other side, you're generating CO2. So this would be CO2. Here, you have hydrogen over here and a hydrogen over here. As a result, you're going to be inserting, right, an oxygen to generate carboxylic acids. Another way to cleave a double bond and add oxygens to it is through ozonolysis. Here's an example of ozonolysis in which you're adding ozone, and second step is dimethyl sulfide. This will cleave that double bond, forming the carbonyl groups, and then DMSO, which is the oxidized DMS, or dimethyl sulfide. Dimethyl sulfoxide is this product over here. Now to note, here you also have a hydrogen. But in the case of ozonolysis, you're not adding another oxygen to form the carboxylic acid. It'll stop at the aldehyde. So it doesn't undergo overoxidation as the concentrated potassium permanganate. So it's milder than that. And then the second step of ozonolysis is the reduction of the intermediate by zinc or dimethyl sulfide. So mechanism of ozonolysis. Again, the crucial part of drawing these mechanisms is making sure that you're putting the alkene and the ozone or the reactants in the right position. And so you want to make sure the two oxygens are nearly above the two carbons, the carbon double bond. Once you do that, it becomes straightforward. Electrons from your, right? Again, electrons from your alkene go to the oxygen, quenching that positive charge. This is, remember, a negatively charged oxygen, so that'll come over here. This will generate a mole ozonide, which is an intermediate. And so make sure you put your double daggers. And so now when you generated this cycle, the next thing is to do more arrow pushing, where now you're going to cleave that bond, right? Electrons go here, electrons to the oxygen go here, and these oxygens come down. So now you've generated two of the double bonded oxygens. In this case, you're going to have a double bonded oxygen attached to another oxygen. Now while this seems normal, this gets trickier, so you're going to have to make sure you position these correctly. You're going to have oxygen from the split, from the carbonyl bearing the extra oxygen, coming and attacking the carbon, the electrophilic carbon. These pushes the electrons here and then adds to this carbon, which then pushes the electrons here. This will generate what is called an ozonide. And that ozonide is what gets cleaved in the presence of dimethyl sulfide, shown here, so that you generate your ketone and your aldehyde, as well as dimethyl sulfoxide. So the ozonide itself is not isolated, but it's reduced by mild reducing agents such as zinc or dimethyl sulfide, as in this case, give aldehydes and ketones as a product. When dimethyl sulfide is used, the sulfur atoms oxidize, forming dimethyl sulfoxide, shown here. So if we compare permanganate cleavage and ozonolysis, here's same starting material. We're adding concentrated version, so you're going to have cleavage here so that you generate an intermediate, again double dagger, where you have on this side your ketone and this side your aldehyde. Remember, because this is concentrated potassium permanganate, you're going to have overoxidation where you have, so this shouldn't be O minus, it should be OH. So please, I'm correcting it for you on the slides. So yeah, so in front of that H, you're going to have that oxygen being added, so you generate the acid. In the case of ozonolysis, you're doing the same thing, a cleavage, but it'll just remain with the aldehyde, not over-oxidizing. So you'll leave with the aldehyde. Okay. So an important thing to note is osmium tetroxide, cold dilute potassium permanganate, and epoxidation oxidize the pi bond of an alkene, but leave the sigma bond intact. Then when you look at ozone and warm concentrated potassium permanganate, that breaks the double bond entirely to give the carbonyl. So let's do a problem. Ozonolysis reduction of an unknown alkene gives an equimolar mixture of cyclohexane, carbaldehyde, and butane 2-one. So if you drew that out, these would be what you draw. Now you want to draw them in a way where you position the ketone or the carbonyl parts where the oxygens are facing each other. When you do this, it makes it easy to say, oh, I see where the double bond came. Double bond came from this part coming together with this part, or when you flip this over in this way. So you can have, remember, if you're going forward, you're going to have cleavage of that double bond forming these two products. So the way to answer this problem, trying to figure out the starting material, is to make sure you face the double bond carbonyls to one another. Polymerization. So an alkene can add to another molecule like itself to form a chain or a polymer. There are three methods: cationic, free radical, and anionic. So cationic polymerization starts with protonation with sulfuric acid, shown here. So the protonation step, I'll draw it out. So you're going to have to first draw out H2SO4, which is sulfuric acid. And then I'm just going to draw OH on this. Oops, sorry, I'm going to move this a little bit so that you can see what's going on. There you go. And then I'm going to add the H. Okay, so the first step is protonation of the isobutylene, in this case your alkene. So you have the electron source from your isobutylene. So it'll come and pluck off that hydrogen, forming HSO4 minus, and forming the carbocation. And the carbocation, so let's move this back. And the carbocation shown here is going to be on the highly substituted carbon. So then that is reactive with another molecule of isobutylene. Again, your nucleophile is from your double bond attacking, and then you generate another carbocation. You continue this cycle until you generate a polymer. This can be quenched where you have HSO4 minus that was generated from the first protonation step, where that will pluck off a hydrogen and form a double bond. So at the end of this polymer, you're going to have a double bond. And that's the termination. So you can also do cationic polymerization using BF3 as a catalyst. So here's BF3 in the presence of water will form this adduct, right? So you have this adduct, and so now the styrene in this case will pluck off that hydrogen, quench that positive charge. This is your products, and here's your carbocation, right, on the highly substituted carbon. Again, you're going to, like before, you're going to have electrons from your double bond come in and attack this electrophile. And so you have another positive charge being generated. Again, this goes again. So then you have the formation of your polymer. You have quenching occurring where the hydrogen, so I'm going to draw out the hydrogen over here and over here from CH2, so you can cross that out. So the quenching will happen when you have this come, pluck that off, form the double bond, and you have at the end an alkene being generated. Radical polymerization now requires formation of radicals, and so your initiation step is crucial. Right, so here's ROOR, which is a peroxide. You're going to have, in the presence of heat, cleavage of that bond. So these are single arrows. So you generate RO radical, and it's that RO radical that reacts. So the rest of the reactions here, you have half arrows shown here, half arrows going to the carbon so that you form a radical at the highest substituted carbon. Again, you have reaction occurring with styrene, so you have the formation of a bond, but again, right, radical formation of that, forming that. So that was what was missing, the half arrow missing to form the radical. So this goes and propagates. You can have quenching reactions occurring where you have molecules already, the styrene already with, that's a radical, just quenching the reaction at the end, which I'll let you do. So for anionic polymerization, you need to have an alkene with strong electron withdrawing groups such as nitro, cyano, or carbonyl. And so here's an example. Here's superglue, which has 2 electron withdrawing groups on this carbon. This allows a base to go and attack and push the electron, so you generate the carbanion. And this is stabilized just because it has these withdrawing groups. With that, you have then reaction occurring where your nucleophile attacks this carbon, pushes the electrons, and continues to go on. And so this would be anionic polymerization. So this ends chapter 8. There's a lot of reactions here, so I encourage you guys to make notes and just keep on practicing these mechanisms, because the only way to do this is just to practice.